Well, hi everyone. It's Wednesday evening again, so it's time for our live stream from Kim Help ASAP. I hope you are doing well this evening. Also hope that my volume is okay. Hopefully my moderator will let me know if everything is all right there. So this week I thought we would do something just a little bit different. We're still going to be working problems, but I know that we are far enough into the semester now that you're probably at least starting to do some labs depending on what class you're taking. And often I have found that students have a hard time shifting from what they do in class to what they do in lab. So I thought we would go over two very common stoichiometry labs. And you might be feeling like you can do the stoichiometry problems in class and on the homework, but when it comes to lab and you're collecting data, you might be a little unsure how to take that data and do the actual stoichiometry problem. Okay, so let's go ahead and get started. So the first lab that I'm going to go through is the combustion of magnesium to form magnesium oxide. This is a really easy lab. You just take a small bit of magnesium ribbon, you put it in a crucible, you heat it up, and you will form magnesium oxide. Now, I'm not going through, obviously, the procedure here. I really want to focus in on the calculations. But this is what you can see on the screen is probably data that you would collect. It should look something like this. So you're going to collect some masses, not only of the crucible, but before of just the crucible, and then the crucible and the magnesium. And then, of course, you have to collect masses afterwards as well. Okay, so the first thing that's important in this lab is, of course, the balanced chemical equation. We must have the balanced chemical equation. Now let's go ahead and get to the data. So the first thing you probably did is you just weighed the crucible on its own. Then you got a small piece of magnesium. You weighed the crucible and the magnesium together. Then you heated this somehow, probably with a Bunsen burner, but it could be done other ways. And then you got a series of weights afterwards. And, again, some labs specify take a certain number of weights, and others specify take weights until the mass is consistent. So you can see here with these masses, I took 4 different masses, and these last 2 masses were consistent, so I stopped taking masses at that point. Now, one thing when you're weighing after doing a combustion reaction where you have heat, of course, you want to make sure that you are weighing your crucible when it is cool. Not only can you damage the balance if you weigh something really hot on it, but having something hot is not going to allow the balance to give you an accurate mass. Hence why you want to wait till it's room temperature. And here in this particular case, I waited until I had 2 masses that were consistent. Okay, any questions before we start our calculations? All right, looks like we're good to go. So the first thing that I want to do is I want to calculate what the mass of my magnesium is. So you can see I've got my crucible and my crucible plus my magnesium. So my first calculation is going to be subtracting these 2 numbers to get just the mass of my magnesium. Okay, so this is going to be just a simple subtraction. So this is my mass of my crucible and my magnesium. I'm going to subtract out the mass of my crucible, and this will give me the mass of just my magnesium. Okay, so I have done that calculation. And this is my grams of magnesium. All right. Now, there are a couple different ways you can go about this. One thing that I like to do at this point, because I know my mass of my reactants is I'm going to go ahead and do my stoichiometry and calculate my theoretical yield. So this theoretical yield is how much you predict you should get if everything goes perfectly. So all I'm doing here is I'm just doing my stoichiometry for this reaction. Now, another thing I do want to note is I do have a limiting reactant. So maybe I should go back to this. So I have two reactants, magnesium and oxygen. Well, the magnesium comes from, the small piece of magnesium that you put in the crucible. But something that might not be so obvious is, where is the oxygen coming from? Well, it's just coming from the air around you. So which one of these is going to limit my reaction? Well, it's going to be my magnesium. I can think of having basically an unlimited amount of oxygen at this point. So once the magnesium has completely combusted, then no more reaction is going to occur. So that's how I determined my limiting reagent for this problem, even though I didn't have an actual mass or number of moles for my oxygen. It's just in the atmosphere. I can use as much as I want. Okay, now let's do our stoichiometry. So I am going to start with my grams of magnesium. So here are the grams of magnesium that I calculated. And the first thing that I need to do is I need to convert that into moles, because when you're doing stoichiometry, of course, you're going to use a mole ratio, which means you cannot be in grams. So this mass of magnesium is easy. You just get it from the periodic table. And again, depending on your periodic table, you might have a mass that's slightly different from this molar mass I'm using, but that should not make a significant difference in your final answer. However, some classes, some teachers and professors do prefer you to use a very specific periodic table, and of course you want to follow those rules. Okay, so now I'm in moles of magnesium. I'm going to use my mole ratio to convert from moles of magnesium to moles of magnesium oxide. And this mole ratio is a 2:2. And 2 moles of magnesium oxide. And then finally, I am going to convert this moles of magnesium oxide into grams of magnesium oxide, because I have all of these masses that I weighed after the reaction was complete. So this molar mass is 40.3044 grams over 1 mole of magnesium oxide. Okay, so I've kind of run out of space there, so I'm going to pop down to the second line. So if you run through this calculation, you will get a theoretical yield of 2.2272 grams of magnesium oxide. Okay, before I leave this calculation, I do always like to show how the units cancel. So you can see my grams of magnesium cancel, then my moles of magnesium oxide, and I'm left with grams of magnesium oxide. Now, the important thing to note here, I think I'm going to keep this in green, is this is your theoretical yield. So this is what you predict you would get if everything goes perfectly. Spoiler alert, very often things do not go perfectly, but this is going to be an important calculation when we get to our percent yield. Okay, now we need to know how much magnesium oxide did we actually get from this lab. So this is our theoretical calculation that we just did, but we went in lab, we got all these masses. How much magnesium oxide did we actually form in the lab? Okay. So this is where sometimes students get confused, because I have 4 different masses here. Which one do I use? Well, you want to use the one that is consistent, And because these last two, I got the same mass when I was weighing, then I consider this my final mass, and I'm just going to ignore these other two masses. Those were not accurate. Maybe the crucible wasn't cooled down enough or something else was going on. Depending on what kind of balance you're using, even somebody next to you who's slamming things on the countertop can make a change in what your balance says, especially for here. Since I have 4 decimal places, this came from an analytical balance, which is super sensitive. So this is my final mass of my crucible and my product, my magnesium oxide. Okay, so let's do that calculation. So I am going to take, I'm going to switch back to blue. I think I'll do it right here. I'm going to take my final mass, that is my 15.5072 grams, and I'm going to subtract out the mass of the crucible, and that will give me my mass of magnesium oxide. So this minus the mass of just my crucible, which of course I weighed at the very beginning of lab. And that gives me a mass of 0.2198. And that is grams of magnesium oxide. Now I want to be really careful because I have 2 numbers associated with grams of magnesium oxide. This is my actual yield. So when I actually went in lab and ran this reaction, this is how much product I got. And just looking at these 2 numbers, you can see my actual yield is lower than my theoretical yield. So when I calculate my percent yield, which I'll do in just a second, I should have less than 100% yield. But they look fairly close. So I'm feeling like, all right, I should be definitely on the high end of the percent yield. It's not like something went horribly wrong and I'm looking at like a 30% yield. So let's go ahead, take our numbers, and calculate our percent yield. Okay, so if you remember, percent yield is simply your theoretical yield sorry, I'm doing this backwards. Apparently it's too late in the day to be thinking clearly. So it's your actual yield over your theoretical yield. And that gets multiplied by 100%. Okay, so let's plug our numbers in for this lab. So my actual yield was 0.2198 grams of magnesium oxide. And my theoretical yield was 0.2272 grams of magnesium oxide. And I am multiplying that by 100%. And my percent yield is 96.74%. So that's a pretty good percent yield there. I'm very close to 100, but I'm not over 100. And so this lab clearly went off without too much of a hitch. Now, one kind of discussion question you might have on this lab is if your percent yield was, less than 100%, where did that mass go? And there are a number of places where it could have gone. I think the most common thing is just loss of product. Depending on how vigorous your combustion reaction is, you maybe could have lost some product that way. you could have lost product at just as you're handling it. Now, this is a very small amount of product loss, so you wouldn't necessarily notice that you had lost it, but that's a very common way to have a percent yield that's lower. The other thing that can happen is maybe the conversion wasn't perfect. Maybe you have just a very little bit of magnesium left and it didn't actually fully combust to form magnesium oxide. That's another problem as well. For a percent yield this high, I wouldn't worry about having improper weighing techniques, but if your yield is very low, you might want to go back and think, did I really weigh these as carefully and accurately as I should have? And that's another place where if your masses are off and they're not accurate, then of course you're going to get a percent yield that is not accurate as well. Okay, so these are generally the typical calculations when you do this combustion reaction to form magnesium oxide. Again, it's supposed to be a way for you to get in the lab and have a hands-on experience with a stoichiometry reaction. And this reaction it tends to be very robust. It's easily reproducible, and it's something that you don't need a whole lot of chemistry skill for. It's a good beginner lab to get your hands-on experience with stoichiometry. So before I move on to the next lab, I just want to make sure that there aren't any more questions. Okay, everything looks great. So let's go on to our second stoichiometry lab. This one is a dehydration lab. Again, it is a stoichiometry lab. It's a very common one. So you take copper sulfate pentahydrate, you let it usually sit in the oven overnight, and you should drive all of the waters off. Again, just like before, I put my balanced chemical reaction at the top of the page, and I have a lot of data here that I have collected. Now, this one is a little bit different in that usually what is asked is if you have fully dried your copper sulfate pentahydrate, or how many waters did you drive off in your copper sulfate pentahydrate, because it's not like all 5 of those waters leave at once. They tend to leave one at a time. So you can, theoretically, you could control, like you could just drive off a little bit of the water. Maybe you just drive off one of the water molecules, maybe 2, maybe 3. So in this lab, we are going to determine how many moles of water did we drive off from our copper sulfate pentahydrate. Just a little bit of a lab technique for this one. It's really important that you grind your copper sulfate pentahydrate really, really well and as finely as you can to get good dehydration. It's sort of like in the summer, if I make a lot of iced tea, and it's much easier to dissolve granular sugar in my iced tea instead of using sugar cubes because I have a greater surface area. So that's a similar thing that's going on here. You can get better drying if your salt is ground really well before you start the lab. Okay, so that's enough on lab technique. Let's start looking at our calculations. Okay, so again, just like before, I am going to calculate how much copper sulfate pentahydrate, or in this case, how much salt that I started with. So I have my mass of my empty crucible. This is a much larger crucible. And then I have the mass of my crucible and my salt together. So I want to know what is the mass of just the copper sulfate pentahydrate. So I'm just going to do a simple subtraction here for this. So here is my mass of my crucible and my salt that I ground as well as I could. And I'm going to subtract it from the mass of just the crucible. Whoops. I skipped ahead there. And this will give me the mass of just my copper sulfate pentahydrate. And I did this calculation, I believe. Okay. going to pull out my handy dandy calculator. Okay, and I get a mass of hydrate of 1.2305. So that is grams of copper sulfate. Ooh, I'm kind of running out of space. Pentahydrate. That should all be on one line, but I'm just kind of running out of space there. Now, just like before, this is a stoichiometry problem, so I'm going to go ahead and convert this grams into moles. So I'm taking my 1.2305 grams of copper sulfate pentahydrate, and I'm going to convert that into moles. And that, of course, is a very large molar mass. And when you're calculating the molar mass for this salt, yes, you do include the waters in this. Okay, I'll come down to my next line here. So that is going to give me 0.00492282 moles of copper sulfate pentahydrate. All right. Now what I want to know is I want to get the mass of how much water actually was lost here. So again, just like before, again, this was a crucible that was heated in an oven overnight. So before you weigh it, you want to make sure that it comes back down to room temperature, and you want to make sure that your masses are consistent before you stop weighing. So you can see again, I weighed 4 different times here, and my weights were changing for the first 2, but then again for masses 3 and 4, I got the same weight. So this is my final mass. And usually just getting 2 masses that match is enough. You could keep going if you wanted 3, but having 2 match means that, okay, everything is settled and this is my final mass. So this is my final mass of my crucible plus the salt that just the copper sulfate salt, depending on, again, how many waters we drove off. So what I'm going to do is I'm going to first figure out what my mass of just copper sulfate would be. So again, I'm just going to do a simple subtraction. So here is my mass of crucible plus my product. And I'm going to subtract out the mass of my crucible. And I have see that calculation. Let me grab my calculator. Okay, so my mass of product is 0.8750 grams. And I'm just going to write product here because I really don't know how many moles of water I've actually driven off. So I'm just going to call it the product. Okay, now I'm going to invoke conservation of mass. I know that the mass I started with has to equal the mass of these 2 products that are formed. I cannot create or destroy mass. We are not using Einstein's equation here. So this mass of my product I can use to figure out the mass of the water that I lost. So again, my total mass here, which I figured out right here, should equal the mass of my product plus however many grams of water that I drove off. So I'm going to figure out how many grams of water have left, in essence. So here is my original mass of copper sulfate pentahydrate. I am subtracting out the mass of my product. And this will give me the mass of water that I, again, have driven off by leaving it in the oven overnight. And that is 0.3555 grams of water lost. Okay, so what we really want to do is we want to compare our moles of water lost to our moles of our copper sulfate pentahydrate. So I've already converted into moles of copper sulfate pentahydrate, but I need to convert this grams of water into moles of water. So let's do that really quickly. Here is my grams of water. And let's get that into moles. And that will give me, actually I'm going to give myself a little more space here. .73 moles of water. Okay, again, that is the water that is lost, that evaporated off in the oven. All right, so if you think about taking this mole ratio, your moles of water lost over your moles of your copper sulfate pentahydrate this should ideally equal 5 because again I'm just pulling this from the mole ratio. There's of course a 1 here that's assumed and a 5 here, so this should be a 1 to 5 ratio, or a 5 divided by 1 should equal 5. So if we have driven all of the water off of our copper sulfate pentahydrate, then we should get a number here that is, again, approximately 5. So let's put our numbers in and let's see if we have driven off all of the water. Okay, so I am going to have my moles of water. And I am going to divide that by my moles of hydrate. 49282. This formula is just so long. Okay, and so when I do this calculation, I get 4.0041, which is approximately 4. Again, I'm looking for a whole number ratio here. Now, the good thing is we did come up with approximately a whole number. So we should have a whole number ratio. You're not going to lose part of a water. You're going to lose either 1, 2, 3, 4, or 5 waters. You're never going to lose like 3.5 waters or 3.2 waters. It's going to be a whole number. So it's good that we got a whole number. However, we were supposed to be driving off 5 waters. So in this lab, we did not drive off all of the water. We only drove off 4 waters. So instead of having a 5 here, we really should have a 4. So what I'm going to do is I'm going to write the balanced chemical equation for my data here, because this balanced chemical equation does not represent what my data says. And because I've got a lot written on the screen, I'm going to write this in green. Okay, so here's my balanced equation. I still started with my copper sulfate, pentahydrate, but I didn't end up with just pure copper sulfate. I ended up with copper sulfate with 1 water attached, or a monohydrate. Or if you wanted, you could have put a 1 in front of there. And I drove off 4 water molecules. So this is my balanced chemical equation based on my data right here. So again, a common question is, all right, so you didn't drive off all the waters. Why didn't you drive off all the waters? And again, there are a couple of things that could have happened. One, it could have been that I did not grind my copper sulfate pentahydrate well enough, and so the crystals were not small enough to effectively drive off the waters. The other thing that could have happened is, did I leave it in the oven for long enough? Another thing is, when you are drying this, you want to make sure you don't have a lid that fits really tightly on whatever vessel you're using. Like, so I was using a crucible, because that'll trap the waters in. So maybe putting the lid on, I put it on a little too tightly so all the waters couldn't escape. Another possibility is maybe I did drive off all the waters, but when I pulled the crucible out, if I say didn't put it in a desiccator to keep it dry, but left it on the countertop, then the salt could have absorbed some water from the atmosphere as well. Again, it also depends on if your lab is really humid or something else happened. So there are a lot of possible errors here for this lab. And in general, if I'm running a lab, I'm not so worried that, well, you didn't drive off all the waters. What I want my students focused on is, why do you think the waters didn't get driven off? Can you point to something that may have happened? Because an important skill to have when you're in lab is to be able to evaluate how you are doing. Are you having good technique? Are you following the instructions properly? Are you following the instructions carefully? And a lot of times that can cause error. But if you have an awareness of what's going on, and oops, I spilled this, now I'm going to have an error, then in general, you're going to be much better in lab than just kind of reading it as a recipe and kind of throwing things together. So that is, again, the second kind of common stoichiometry lab that you run across is this dehydration of copper sulfate pentahydrate. And here is how you do, again, the most common calculations for it, and, obviously the most common discussion questions. So we're gonna sign off a little early today, unless there are any more questions about this. Let me know what you think about doing labs for the live stream. Again, I know some students have had trouble with getting through calculations for lab, so I'm happy to do lab type calculations as well as work other problems as well. So thank you so much for joining us tonight, and I hope to see you next week.